Hello, and welcome to our lesson on the surface area of compound shapes in 3 dimensions. In this lesson, we will learn how to integrate simple nets into compound shapes to visualize and calculate their surface areas. The lesson will be structured around 3 key examples. In our previous studies, we have learned about different kinds of 3D shapes. We have also learned how to calculate the area and perimeter of 2D shapes. In addition, we have practiced using basic nets to calculate the surface area of simple 3D shapes. With this strong foundation, we are now ready to tackle the creation and use of compound nets. This technique is incredibly useful in various practical scenarios, such as packaging design, where understanding the surface area of combined shapes is crucial. Let's delve into this topic and develop our understanding of geometric surface areas. Let's get started with our first example. Here we have a cube with a pyramid sitting on one of its faces. Our goal is to find the total surface area of this composite solid. To do this, we break the problem down into simpler parts. We start by considering the cube and the pyramid separately. For the cube, we need to remember that one of its faces is covered by the pyramid, so this face won't be the part of the surface area calculation. Similarly, for the pyramid, its base is covered by the cube and thus not part of the surface area. Let's first deal with the cube. A cube has 6 identical faces. Each face has an area of side length squared. Since one face is covered by the pyramid, we only consider 5 faces. So the total surface area of the 5 faces is 5 times side length squared. Let's now consider the pyramid. A square-based pyramid has one base and 4 triangular faces. The square base is covered by the cube, so it isn't part of the surface area. Each triangular face has an area of half times base times height. Therefore, the surface area of the 4 triangular faces can be written as 4 times half times base times height. Finally, we combine the two. We find that the total surface area of the composite shape equals the surface area of 5 cube faces plus the surface area of 4 triangular pyramid faces. So we get a final answer of 5s squared plus 2bh. Let's now consider a hemisphere mounted on one face of a cube. Our task is to determine the total surface area of this new composite solid. Again, we'll break this problem down into parts by considering the cube and the hemisphere separately. For the cube, acknowledge that the face on which the hemisphere rests is not entirely part of the surface area. Similarly, for the hemisphere, the flat circular surface that connects with the cube is not part of the surface area. Let's now deal with the cube's surface area. Like before, the cube has 6 identical faces, but one face is partially covered by the hemisphere. Each face of the cube has an area of side length squared, but we need to subtract the area of the hemisphere's base. The area of the base of the hemisphere is the same as the area of a circle, using the radius of the hemisphere. So we get area equals pi r squared. Therefore, the included surface area for the cube equals 6 times side length squared minus pi r squared, where r is the radius of the hemisphere. Now let's move on to the hemisphere's surface area. A hemisphere comprises a curved surface and a flat circular base. The flat base is covered by the cube, leaving us just the curved surface to calculate. The curved surface area will equal half of the surface area of a sphere. Since the formula for the surface area of a sphere is 4 pi r squared, then the curved surface area of the hemisphere is 2 pi r squared, where r is the radius of the hemisphere. Finally, we combine the two to find that the total surface area equals the surface area of 6 cube faces minus the base of the hemisphere plus the curved surface area of the hemisphere. So we get an answer of 6s squared minus pi r squared plus 2 pi r squared. This can be simplified to 6s squared plus pi r squared. Let's tackle another compound shape, but this time with specific lengths. Here we have a cuboid with dimensions 3 centimeters by 3 centimeters by 5 centimeters, and atop it a pyramid with a square base of 3 centimeters by 3 centimeters and a height of 4 centimeters. Again, we'll break this problem down into its components and consider the cuboid and pyramid separately. We can see that one face of the cuboid is covered by the pyramid, and the base of the pyramid is covered by the cuboid. Let's begin with the cuboid. The net of this shape consists of 4 larger rectangles with side length 3 centimeters and 5 centimeters, so each of these faces has an area of 15 centimeters squared. The net also includes 2 squares with side length 3 centimeters. Remember, one of these faces is not included in the surface area because it is covered by the pyramid. So we just count one face with an area of 9 centimeters squared. Adding these up, we find that the total surface area is 4 times 15 centimeters squared plus 9 centimeters squared, which equals 69 centimeters squared. Moving on to the pyramid, let's examine its net to calculate its surface area. We do not count the base of the pyramid because it is covered by the top face of the cuboid. So that leaves us with 4 triangular faces. Each triangle has a base of 3 centimeters. We know the height of the whole pyramid is 4 centimeters, but the height of the individual triangles is unknown. To calculate the area of each triangle, we first need to calculate the height of the triangular face. To do this, let's go back to the pyramid. We can draw this right-angled triangle to help us find the triangle's height. We can see that the height needed is the hypotenuse of this new triangle. We can find the needed height using Pythagoras' theorem. The height of the pyramid's triangular face is the hypotenuse of this triangle, so we solve for c by substituting the known values in to find that the height equals the square root of 1.5 squared plus 4 squared. This equals the square root of 18.25, which is approximately equal to 4.27 centimeters. Now that we know the base and height of the triangle, we can calculate the area using the formula half times base times height. Therefore, the area of one triangle is half times 3 times 4.27, which equals 6.405 centimeters squared. So the total area of all 4 triangles is 4 times 6.405, which gives a total of 25.62 centimeters squared. Adding the areas of the cuboid and the pyramid, we get 69 centimeters squared plus 25.62 centimeters squared, which gives us a final answer of 94.26 centimeters squared. By working through these examples, we see how to break down complex shapes into their simpler components, create their nets, and calculate their total surface areas. This method allows us to tackle even more complicated geometric problems with confidence. That's the end of the lesson. Great work today! We explored the fascinating world of compound nets and saw how they are instrumental in determining the surface area of combined 3D shapes. By breaking down complex shapes into simpler components and visualizing their nets, we learned how to effectively compute their surface areas. With practice, these skills will become intuitive, enabling you to tackle even more intricate geometric problems with confidence. See you in our next lesson.